Welcome to Hartman Math. This is lesson 3.3, Building Polynomials, part 2. We're taking a look at graphs of power functions, x to a power, where that power is a positive integer, like 1, 2. It's back from unit 2, 3 that we've seen so far, but we could even go higher. We're just looking kind of for patterns. So the first one we're looking for is f of x when x is an even power, like 2 or 10 or anything like that. And there's going to be a lot of similarities in those graphs. So we're just going to really focus on x squared, the one that we know back from unit 2 that has a vertex at the origin. Right one up 1, same on the left. Right one up 3, same on the left. And there's our parabola, our quadratic function. And it turns out that x to really any even power is going to really resemble this graph. Especially it's going to have these key points here. Now these can change. The bigger it gets, the faster it grows, but it's definitely going to have the same shape, which means it's going to have the same domain and the same range. The domain, negative infinity to positive infinity, all real numbers. The range starts at 0, bracket 0, comma, up forever, positive infinity. So the next thing we want to think about is the end behavior. What does it look like as we go right on the graph? What does it look like as we move to the left towards negative infinity on the graph? Think of that as we switch over. So our end behavior for f of x equals x squared, the one that we showed, or x to the 10th, or x to the 6th. As x approaches positive infinity, the function is approaching positive infinity. As x approaches negative infinity, f of x is approaching positive infinity. Informally, what that means is, out on the left, starts high, go through our graph, ends high. So that's going to be the end behavior. Starts high over here, ends high over here. Let's look at an odd power function, like x to the 3rd. That was our parent function for this unit, for cubic functions. It could also be x to the 7th. It's going to be very, very similar. We know that we had, as we kind of create a table of values, 0, 0, 1, 1. If I cube 2, 2, 8, doesn't quite fit here, but it would be about there. And here, changes the direction of the bend at the origin, so there's our inflection point. So there's our graph. What's the domain there? Left forever, right forever. What's the range? Goes down forever, goes up forever. And these will be true for any odd power function like x to the 3rd, or x to the 1st, or x to the 17th. So formally, our end behavior, as x approaches infinity, going to the right, our function is approaching positive infinity. As x approaches negative infinity, going left on the graph, left, we're approaching negative infinity. Not a very good symbol there. Informally, that means on the left, it starts low, does some stuff. On the right, it ends high. Starts low, ends high. So once again, we're going to be focused on graphing from intercept form, also known as factored form, which we've already been doing. Previously, we used sign chart. Later in this unit, we'll start in polynomial form and use some factoring techniques to get it into factored form. But it's going to be factored form if our function is some multiple a value. We already know what that means. A means it could flip it upside down. Okay, it could make it narrower by stretching it vertically, all of that. X minus x1, meaning x1 being a root or a zero of the function. X minus the second one, x minus the third one, and so on. So that's our form. We kind of saw it in quadratics, listed as x minus p and x minus q. It's the exact same idea. So we call that intercept form. So here are going to be our steps when we're trying to graph a polynomial from that, maybe without using a sign chart. So to determine the degree of the function, the number of linear factors. So if we were going to multiply it all out, how many x's are being multiplied, that's going to end up being our degree. We just saw our end behavior stuff. So even degree is going to start high and end high, like x squared. Odd degree is going to start low and end high, start low, end high, just for our parent function there. Then we're going to have to take a look if the a happens to be negative. We don't really care on these. You're going to see we're not really going to care so much about the y coordinates, how far up the graph goes or anything like that. We're just focused on where are we above the x-axis, where are we on the x-axis, where are we below the x-axis. So the a, although it could be 2, 3, 4 like that, we know that that stretches it. We're really not focused on that. We're just really focused on if a is negative, is it going to flip our graph? So if it was even, it would flip from starts high, ends high, flip it to starts low and ends low. And with our odd degree, if a is negative, it's going to flip from starts low, ends high to the opposite, starts high and ends low. We're going to find the x-intercepts there, essentially, or the roots. So listing those, we're going to list them in a table format, which you're going to see in a moment. List those, and then we're going to see the multiplicity of each of those factors. So does one of these factors have an exponent? Is that exponent even? In which case, officially, the graph is tangent to the x-axis, but it really just means that the graph is going to bounce off. Like x squared, if you look at that parabola, on the x-axis, it touches the x-axis just at 0, comes down and just bounces off. That's the idea, and that's the shape that we're looking for. But if it's an odd multiplicity, like x to the third power, where we have that point at the origin, and the graph goes from below to above, and it crosses right through at that point. So we'll again focus on that. So we're looking for those multiplicities. Here's example number 1. We want to sketch the graph of f of x. We start with the degree of the function. Essentially, if we were going to multiply this out, we would have x to what power as the highest exponent? Well, we'd have to square x there, so that's x squared, times another x, makes x to the third power. And that means that our degree is 3, which is odd. So typically, the end behavior would look like our parent cubic function. Starts low, ends high, starts low, ends high. Now let's look for the a. Is it negative? A in front, I don't see anything. It's just a positive 1. So the value is 1. Is that negative? It is not negative. So we're not going to flip it. So the official, real end behavior is going to start low and end high. All right, let's look for the roots. This is x minus what number? 4. Look inside, think opposite. The root is negative 3. The multiplicity, this factor, has an exponent of 1. And that's an odd number. According to our chart there, when we have an odd multiplicity, the graph is going to cross at -3 on the x-axis. All right. Ooh, this factor also, there's its exponent, that's its multiplicity. Multiplicity of 2. The root is +1. Since it's an even, we're going to bounce. So let's immediately put our roots. -3 translates to an x-intercept at -3, 0. +1 means there's an x-intercept at 1, 0. Outside of that, we know that we're going to go to the left, start low. Outside of this, we know we're going to finish high. So as we come up towards this at -3, it says that we should cross through the x-axis. Kind of missed there. Cross right through the x-axis. Now we're going to have to start bending back towards the next x-intercept. But this time, when we hit at +1, 0, we're going to bounce. And that needs to be a rounded bounce, like the bottom of our parabola. So rounded bounce. And then remember, we finished high. So bounces cannot look like this. No polynomial function has that sharp corner. So, nice, smooth, rounded everywhere for our polynomial functions. I think that's our graph for f of x. Here's example number 2, a graph of new f of x. Remember the things that we started with. What's the degree? X times x times x makes x to the 3rd power. Degree is 3. That would mean our end behavior typically would be, for an odd, starts low, ends high. What about A? -1, which is negative. We're just going to flip our graph. It was low to high. We flip the whole thing. Final end behavior, official end behavior, starts high, ends low. Now let's create our table. We've got roots. We've got multiplicity. We've got behavior. Ooh, that one's a tricky one. X as a factor means there is a root at 0, because x is the same thing as x minus 0. 0, 0, x-intercept. The multiplicity, an invisible exponent of 1. Since that's odd, we're going to cross. Right here, the root is -2. Also with an exponent of 1, meaning for the factor. So the multiplicity is 1, and that's also a cross. And out here, -4 to the 1st power is for that factor, so that's a 1, and that's also a cross. They're all crosses. So point here, left of -4, it's going to start high. Right of the final x-intercept 0, it's going to finish low. And we're going to cross everywhere. So we're going to come down and cross, cross, cross. Crossed on all of them. So that's example 2. Example number 3. Degree x. That x is going to get squared, so x times x squared makes x to the third. That's degree 3. So our end behavior unofficially starts low like x to the third power, ends high. A equals -2. Care about the 2? Not really. Do we care about the negative? Yes, we do, because that's going to flip our graph. Our official final end behavior starts high, ends low. Let's make our chart. We've only got 2 factors. So we've got root, we've got multiplicity, we've got behavior. A little long there. All right, first one, our root is +1. The multiplicity is the exponent for the factor. Invisible 1. That's an odd number, so we cross. What about this as a root? 3. What's its exponent for that factor? Right there. It's a 2. That's an even number, so we bounce. So let's plot our x-intercepts at 1, 0, 3, 0, and our end behavior left of the furthest leftmost x-intercept, we're going to finish high. Right of the furthest right x-intercept, we're going to end low. So we're going to come down to 1, and it says we're going to cross. And then we're going to bend back towards 3, 0. When we do that, we're not going to cross. We're going to bounce. Well, let's just say for a moment that we did cross accidentally. And then I said, well, I know I'm supposed to do this, so how about I just do that? We can't do that because I'm going to come around and say, what happened right here? There are no factors that lead to that as a root. There is an error. So can't cross right there. We have to bounce, very rounded bounce, and finish low. It's now your turn. Go ahead and pause the video here until you got your graph. We'll check and see how you did. Our degree, x squared times 1 more x makes x to the third power. Degree is that highest exponent of 3. That means our unofficial end behavior starts low, ends high. A equals a 1. 1x squared in front. So the official final end behavior, no reflection. It's not negative. We're going to start low, end high. Our table, we've got factor, factor. So 2 factors lead to 2 roots. So we'll go root, the tricky one, root, coming from a factor of x, root is 0, leading to 0, 0 on our graph. Multiplicity right there. Since it's even, what does it do? Bounces. Right there, we've got 2. Its multiplicity is its exponent, which was an invisible 1. That's an odd number we cross. 2, 0. End behavior, left of here it starts low. Right of here it ends high. As we come up, what happens at 0? It's going to bounce. And we've got to bend back till we get to number 2. But there it's going to cross. And there's our graph. And that's it for today. I'll see you next time.